The aim of this lecture is to try and present a brief summary of the historical evolution of the subject we know today as rock engineering, which is the building of structures in or on rock masses. I'm going to take you through a series of slides that illustrate some of the key development points in this history. This slide shows a tunnel in Greece that was constructed 2,500 years ago to bring water to the city known today as Pythagorean on the Greek island of Samos. So rock engineering has been with us for a long time. What's remarkable about this tunnel is that it was started at both ends and met in the middle. So it's really more a success story about surveying than about rock engineering. But nevertheless, there you see that the subject has been around for a very long time. In the early days, it was generally soil that was the problem. So if you were building a building and the foundation was on soil, you tried to go down until you hit rock. And when you hit rock, the problem was at an end, and you assumed there were no difficulties with the foundation. And it was not unusual to assume that rock was infinitely strong, as you see in this slide taken in BC in the 1920s. There was one area where there was a serious problem with rock, and that was in very deep level mines in the Kola gold fields in India and in the deep level gold mines in South Africa, where they were mining at depths of in excess of 2 kilometers, sometimes 3, and where the rock stresses are so high that the rock effectively implodes into the excavation you've created. And that's known as a rock burst. Not a lot was written about it because this was an embarrassment to the mining companies. A lot of miners were killed in these events. And so relatively small groups were assembled to try and sort out the problem. And the evolution of that was a very long one, and it still goes on today because we still really don't have a means of predicting accurately or preventing these damaging events. The one thing that was unique about them is that they were generally in very hard, good rock. The discontinuities of the rock were tight, and so the whole subject was treated from an elastic point of view. The role of the discontinuities or the joints or the faults in the rock were not really an issue. So all of the early literature of the subject dealt with rock as a engineering material, rather like steel or concrete, which is a little bit artificial, but that was the history. And although we learned a lot, we had to supplement that in later years with the introduction of discontinuities. So there were tests done in a lot of laboratories around the world, particularly geophysics labs in the United States, where a lot of excellent work was done on the properties of intact rock, in their case for the purpose of earthquake prediction, in our case in rock engineering, to gain an understanding of the behavior of the rock. And so this is an illustration of one of the triaxial cells that was used to test, as you see there, a sample of diamond drilled core of rock, which is tested under confinement with various gauges attached to it. We had no computers in those days. Personal computers really only became available in the 1980s, and in the late 50s, 60s, 70s, we had to make do with other tools. One of the most powerful of those was photoelasticity, in which if you view a stressed transparent body in polarized light, very often you'll see colored fringes, and you see this quite frequently in the windscreen of a car in certain lighting conditions. But this is a very precise tool, and this slide illustrates a high-capacity frame in which we're able to load glass plates of about 15 centimeters square under very high loading, and by ultrasonically drilling cavities into the glass plates, you could study the behavior of cracks or tunnels or whatever you were interested in. And on the right there you see a photoelastic pattern showing stress distribution around a circular hole, and you'll notice that there are vertical cracks in the top and bottom, in the roof and floor of that simulated tunnel. And this technique played an important role in understanding the mechanics of how cavities behaved in rock masses. The rock masses, remember, were in those days considered elastic, and so we didn't have the tools to do anything else. One of the things that did concern us a great deal was the difficulty of incorporating gravity into our theoretical models. And we had theoretical models which are solved by traditional methods of log tables and calculators, slide rules, a very tedious process, but it was very difficult to include gravity in those calculations. And so the idea arose that we could use a centrifuge to simulate gravity. And this is a centrifuge built in about 1960, 3 meters diameter, 1,000 G capacity, so you could increase the gravity on a model by a factor of 1,000. And you see in the lower part of the slide a plaster of Paris model of a mining sequence with uniform loading on the left and gravity loading on the right, and the failure patterns are quite different, as you would expect. And so these kind of tools helped us a great deal in understanding how failures propagate in intact materials. Centrifuges are not really used in rock mechanics these days because even with 1,000 G, you can't break intact rock. And if you're dealing with a discontinuous rock, it becomes incredibly difficult to construct a model that's going to survive a centrifuge test in any meaningful way. They are very heavily used in soil mechanics for testing all manner of structures and simulating failure and behavior of soils. There were other kinds of models used in those days, and the one on the left is a large model that was built at Imperial College in London for testing jointed rock slopes, and gravity was simulated in this way, in this model, by constructing the model on a glass plate horizontally, and then putting another glass plate on top of it, and turning it into vertical position. So gravity was turned on by simply rotating the model vertically, and as you can see in the slide, failure of the jointed rock slope was created. The lower right is a model looking at the behavior of coal mining roadways, and you'll see the coal pillar right and left of an opening, and the timber struts very realistically constructed at a relatively small scale in the model. So we went along for many years, really playing, if you like, with the peripheries of the subject, but learning a great deal about the mechanics on the way, until the 1960s, where this was really a wake-up decade for rock engineering in both mining and civil engineering. And this slide illustrates a dam in France, the Malpasset Dam, which failed in December 1959 during filling of the dam. And it's a concrete arch dam, so you're looking upstream at the reservoir, you're standing downstream of the dam. And the failure was caused by a fault within the reservoir, which seemed to be safe when you looked at the mechanics, but the loading of the water pressure created as the reservoir was filled caused that fault to slip and the dam to fail. A more serious failure occurred at Vajont in Italy in 1963, and here you see the dam on the upper left being the dam's concrete arch dam being impounded, and the reservoir behind it accumulating. And in the background, you see a white scar on the mountain up here. This mountain is called Mount Toc, and you see a white scar there, which illustrates instability. And the general consensus at that time is that this would not be a problem in the filling of the reservoir. That proved to be wrong, and the lower right you see with the consequences of a massive slope failure, where the reservoir was almost completely filled with debris. It caused the water to overtop the dam by 100 meters, and miraculously the dam remained. But downstream of the dam, the town of Langarone, which you see before the failure on the upper left, and the lower right shows the complete destruction of the town, and 2,400 residents were killed in that flood that resulted from the overtopping of the dam. In the mining field, a lot of coal mining, for example, was done by room and pillar mining, where the coal seam, which would be horizontal, is extracted by removing a cross pattern of tunnels, leaving a pillar at each intersection. And the tendency is to rob those pillars because that's a valuable resource you're leaving in place. And in many cases, the estimates were wrong and the pillars failed. I don't have a photograph of the failure that occurred in South Africa in about 1963. A coal mine collapsed and instantaneously killed 430 miners who were underground at the time. I don't have a photograph of that, but I have a photograph of a mine elsewhere, metal mine, and this is what it looked like. Here are the pillars, and that's what it looked like at surface after the failure, which actually occurred while I was underground. We had driven in the morning, parked on the paved area that you see there, overlooked the valley, then we'd changed and gone underground. And while we were underground, it became increasingly evident that things were not going well. So we were all evacuated, and when we got onto the surface, the parking lot was gone, and there was a big hole in the ground. So that kind of failure is a very serious event, and it occurs more frequently than we like to admit. But these events, all of them, the dam failures, the underground pillar failures, were a wake-up call that we were really pushing rock to its limits, and we had to do something more serious than playing with the toys that we'd used up to that point. At that time, most of the problems, as I said earlier on, were soil-related. So when you drilled typically for a foundation, you drilled down until you got half a meter into the rock, and you said, that's it, we're not going to do any more drilling, we've got enough information. So the techniques for drilling in rock were very poorly developed. The machines were hopelessly inadequate. There was no real method for storing the core securely, and you see on the right there a core in Sri Lanka on a dam project which had been vandalized and is of very little use for gathering information. Fortunately, over the years, due to a lot of pressure from clients and consultants, the drilling industry improved enormously. And today you can demand core in almost any location and expect and receive almost 100% core recovery. So that problem has been largely overcome. So today, in visiting a large project, you would very often see the core laid out, and in the lower right there you see probably several kilometers of core laid out, very high quality core, and that is mapped then to determine the characteristics of the intact rock and of the discontinuities that occur in the rock mass as you drill through it. When we look at the impact of discontinuities on the behavior of a rock mass, which is almost exclusively the topic that we deal with today, so we have the intact rock behavior there as the core, but the behavior of most engineering structures in rock are controlled by the discontinuities. We have to consider the issue of scale, and I'll come to some large-scale issues in a moment, but starting at this sort of pattern where you have a very densely populated joint pattern in a rock mass. This is a volcanic area where there's been a lot of fracturing of the rock due to tectonic activity and a very large number of joints closely spaced. So when you stand back from that and you consider building a tunnel or a slope in that, it almost looks like a homogeneous rock mass, like a sandy soil with very big grains. And so in the early days, we were able to do quite a lot of work by assuming that rock masses were homogeneous, uniform in their behavior. And this then led to the evolution of a number of classifications. Remember, we're still talking about the days when computers weren't available. We're still looking for techniques for gathering and interpreting information that have to be rather simplistic in their nature. One of the best classifications is a qualitative description of rock masses by Terzaghi, in 1946, and it's still worth looking at the words that he wrote to describe what he visualized different rock masses would do, how they would behave in tunneling. Then the classifications tended to become a little more quantitative. In 1958, Laufer in Germany produced a classification for the stand-up time. How long do you have to work in a tunnel before it falls on your head? And then the most quantitative effort was by Deere in 1963, where he produced the rock quality designation, which was a measure of the number of intact core pieces longer than 10 centimeters that you get in diamond drilling a core. So if you had 40 centimeters of pieces longer than 10 centimeters in a 1 meter core, the RQD of that core would be 40%. And then followed a number of classifications designed primarily for the estimation of support in tunnels. 1972, Wickham and Company, 1973, Beniowski, 1974, Barton, 1977, Loebscher, and they all followed a similar pattern with an increasing number of parameters, all of which were estimated or measured from core or from observations in the field. 1980, there was the introduction of a different type of classification or characterization by myself and Brown, and this aimed to provide from qualitative descriptions of the appearance of the rock mass a table or a chart which enabled you to estimate the rock mass strength and deformation characteristics. One of the best constructed classifications was in 1990 by Pearson and Company in the United States for rockfall hazards in highways. And it includes a number of factors other than geological, including line of sight and speed of vehicles and so on. So it's a very comprehensive classification used for designing against rockfalls. And finally, an additional one by Palmstrong in 1995. These were all very important developments and enabled us to move things ahead, to estimate parameters, to estimate tunnel support, and are still used extensively today. One of the things they did do was to give us a feel for what the properties of a jointed rock mass might be. And so here are a number of plots from the different classifications, the top one showing the ratio of the rock mass strength to the laboratory strength. In other words, how much is the intact specimen you test in a laboratory degraded by the presence of discontinuities. So they would go up to 100% on the right-hand side, meaning intact rock, and as the rock mass rating or the geological strength index or Barton's Q rating decreases in value, the strength decreases. And similarly, the lower right is for the deformation modulus. How much does that decrease in terms of rock mass quality? These then, for the first time, gave us, together with the evolution of computer software and hardware, the ability to do some fairly serious stability analyses. This is a fairly recent example, but it illustrates the principle of where we were in the, I would say, the early 80s and from then on. This is a large rock slope shown in the lower right there, which is actually a flow of andesitic lava from a volcano inland on an island, and that lava flowed over a weak marine sediment. So you have quite a strong jointed rock mass resting on a very weak marine sediment base. And so this represents, the slide you see there represents a probabilistic analysis of the factor of safety of that slope for different conditions. So there were 5,000 attempts were made there, varying the properties of each of the component materials within a distribution, and producing a factor of safety diagram seen on the upper left. A factor of safety 1 implies failure, and so that gives you then the red part of the distribution curve. If you take the area of that divided by the total area, you get the probability of failure, which in this case is 18%. So this introduced us to A, the ability to do serious stability analysis, and B, the beginnings of what today is very commonly done in rock engineering design, the use of risk analysis. Risk, as shown in this matrix, is a function, is a product of hazard, which is the probability of failure, and consequence. It's no good calculating the probability of failure if you don't know what the consequences of failure, of that failure will be. So you could have, for example, as the case we've just analyzed, a moderate hazard, 18% would be a moderate hazard, but very high consequence, and that means you'd be in this box of risk. And similarly, you could have a very low hazard with low consequence that you don't have to worry about. This has been summed up in this diagram, which is very often called the ALARP diagram. ALARP meaning as low as reasonably practicable. So if you look at that diagram, the increasing risk is on the vertical scale, and you have negligible risk at the bottom where you'd be in very good rock, shallow depth, easy construction. And then as you go deeper and deeper, the rock burst problem we talked about earlier on would be at the very top end there, where you don't go there unless you really have to. And in the middle is the area, the ALARP area, and the question that you have to then assess as you're designing a structure is, how much money do I have to spend in order to make the risk of that structure acceptable? This is a plot and there are many, many versions of this, but this one was put together by the Australian National Committee on Large Dams, and it shows in the red plot at the bottom there, the ALRP risk that is considered acceptable for major structures today. This point here is an interesting one because that is the risk of an individual, you or I, living a normal life, not doing skydiving or extreme sports, but living a normal life. That is the risk of being hit by a bus or having a heart attack or whatever, 1 in 10,000 per annum. And so that's considered the pivot point for most of these diagrams. And as the number of fatalities increase here, so this is annual probability of occurrence of N fatalities plotted against N fatalities. So obviously you want to stay, if you can, within that diagram or below it. The squiggly lines here are historical, built on historical data and refer to fatalities that have occurred in fires, in landslides, explosions, as they've been identified on the captions. And clearly all of those are unacceptable, so you try and if you can, stay below that. There are some circumstances where you might want to go above the upper red line there. For example, in an open pit mine, you have very tightly controlled limited access. Only people who have gone through rigorous training are allowed to enter the property. There is continuous monitoring of displacements, of many things. There are evacuation plans. And so under those circumstances, it's justifiable to go as high as you can justifiably go for the risks involved, but certainly over the red band there. So the risk, whole risk process is becoming increasingly important and will become a dominant part of rock engineering in the future. The big issue is where do we get the data from? Because we're not dealing with man-made materials. We're not dealing with steel or concrete. We're dealing with what you're given in a rock mass and the factors that have influenced it over geological time, the earthquakes and the plate movements and so on. And so it's a highly variable material and we have to accept that. So we're always going to be data deficient in our construction of these kind of diagrams when applying them to rock engineering. And then we come to the question of scale I mentioned earlier on. So far we've just looked at rock masses that we can treat as homogeneous. But if you have very large structures like faults, shear zones, or continuous joint planes, these can dominate the whole behavior. And in the upper left, you see a cut, it's called a cut and fill stope, which is an excavation created to mine an ore body, and its shape is controlled entirely by the two major parallel structures you see there, the bedding planes, top and bottom, and the cross jointing. So that's not a mistake, that's how it is mined, to take advantage of the natural control of those features in the rock mass. And on the right-hand side, this is in the foundations just below a major arch dam in Tasmania, and you can see that the horizontal bedding planes there would have been critical in evaluating the stability of the foundation. So what do we do in order to incorporate this into our geotechnical models? We call this model a discrete fracture network, and in simplistic terms, in the upper left, you see an isometric drawing of a number of intersecting discontinuity features, joints or faults or shear zones. And in the real world, this is what it would look like. This is a large open pit mine in Chile, which I'll show you in a moment. And you can see the myriad of discontinuities crisscrossing there. And that is the joint fracture network that we have to contend with. The dark blue fault running, trace running right through there is the major fault that runs right the length of Chile and is the source of most of the mineral. This is a copper mine. Looking down on an isometric drawing of the open pit as it is today, you can see the traces, that means where these features intersect the surface, of the myriad discontinuities that occur in that rock mass. This mine is 4 kilometers long in the vertical axis, 3 kilometers wide, and 1 kilometer deep. And so there's a lot of rock there that has to be dealt with. And one of the examples I'd like to quote in this lecture to illustrate how it's dealt with today is this one here, which concerns the stability of this block of rock here. That slope that you're looking at there is about 300 meters, the top 300 meters of the 1,000-meter pit, and the concern is how stable is that block. The process that is used here is to map the structures from either mapping along the benches or from core, and to build up a discrete fracture network and pictures such as this one where you know the features are, and then to incorporate those into three-dimensional discrete element models, of which this is one. So the top left is the mesh network used to create the three-dimensional model of that slope. The middle one is the distribution of rock types, because there are many rock types that occur in that rock mass in that model. And the lower right is the superimposition of the major discontinuities, the ones you saw as long blue lines in the previous slide, into that model. And that model, which is a very complicated one to construct and to run, produces then the behavior of the rock mass. And what is illustrated here in the colored contours are the horizontal displacements in that part of the slope. In order to calibrate that, which you have to do with any numerical model, this particular mine, Chuquicamata in Chile, has been in operation for a century, and for the last 20 years has had a very extensive network of monitoring displacements. So you have two systems in place. One is a distance measuring device based on laser beam, which is shot to a target, a mirror target, and the travel time is measured between its exit and return. And there are 1,000 monitoring points around the slope, and there are 6 monitoring stations with automatic distance measuring devices, and those scan the pit on a regular interval, so it's under constant surveillance. Where a zone of instability is shown in the general picture, that can then be focused on in much greater detail by radar equipment. And there are a number of these devices which are radar transmitters which send out a radar beam and which look at the rock itself, not a target, and measure the return time for movement of the rock face. And you see here contours of displacement which match those predicted in the numerical model. So over the years, the technique for monitoring and modeling have gone hand in hand. And the net result of that is a process where if you know that there is instability, you can plan to do something about it. You can plan to divert your mining activities, to take the failure out, or do various things. You can't reinforce it on this scale because the slope is simply too large. So this is the Chuquicamata mine today, probably the world's biggest open pit mine. As I say, it's 4 kilometers long on this axis, as you're looking at it, 3 kilometers wide and 1 kilometer deep. And the little dots that you see on the highways there, that one there, for example, is a 400-ton capacity truck. So that gives you a feel for the scale of the whole operation. About 500,000 tons of rock are mined every day in that mine. So where do we go from here? In the early 2000s, the concept was introduced of what is now called a synthetic rock mass. And this has been evolving in many centers around the world, but the most intense development has probably followed from the work of a man called Kundal in the US. And what that does is it looks at a numerical model where you can take a discrete fracture network, shown in the upper right there, integrated with the blocks in between the discontinuities, which are then modeled separately, as illustrated on the left-hand picture of a compression specimen, and produce a model which looks at the behavior of both the discontinuities and of the intact material. We have a great distance to go on this, but it opens up huge possibilities of much more sophisticated modeling than we've done in the past, and much more productive and interactive design processes. The big problem is data deficiency. Where do you get the data to populate these? And the other problem is computer capacity, because as you can imagine, you need huge computer power and very sophisticated software to do these kind of models. And just as an example of where we might be going, this comes from work done under the direction of Professor Derek Martin in Alberta in Canada, where he's modeling down to grain scale. So the upper left shows pictures of grains in a granitic rock mass, up down to 1 millimeter in size. And these grains have individual properties, and their sizes are distributed according to the size distribution in the rock itself. The contact strengths can be modeled, and that then produces results which are increasingly approaching those that we actually measure or detect in the field. So the lower right there shows some three sketches, 3 pictures from an experiment in southern Sweden, where in the nuclear waste industry there, they're looking at the disposal of nuclear waste in crystalline rocks deep underground. And one of the big issues there is the fact that when you put nuclear waste in the ground in the first place, it's very hot. And so you induce thermal loading in the rock from the waste before it decays in radioactivity. And you can see the first slide there, model from this model up here. You can see little marks on the screen there which indicate either tensile or shear failure. And those then match pretty well the observations which are sketched in the middle slide and the photographic evidence that you see on the right. We're not there yet, but it's indicative of where we will go as our skills in gathering data of building software, and hopefully the hardware industry will meet our needs for much, much greater power than we have today.